Today, we're going to talk about something really cool. We're looking at how scientists are taking simple yeast and turning them into these tiny living factories. And their goal? Well, it's to brew the chemicals we use every single day, but in a way that doesn't rely on fossil fuels.
So let me ask you this. What in the world does your face lotion have to do with fossil fuels? It sounds kind of random, right? But the answer actually points to a massive problem that's hiding in plain sight on pretty much every store shelf. It all comes down to one key ingredient, and where we get it from is, well, it's not great. So let's get into it.
All right, so before we can really appreciate the clever solution these scientists came up with, we have to understand the problem they were trying to solve. And it all starts with an ingredient you've probably never heard of, but you almost certainly use every single day. And that hidden ingredient is a group of chemicals called fatty alcohols. Now, these things are the real workhorses of the chemical industry. They're what make your lotions feel smooth, they give your detergents their cleaning punch, and they're in everything from plastics to industrial lubricants. Seriously, they are everywhere. And here's the real kicker. The way we make the vast majority of these fatty alcohols is problematic. We either get them from petroleum, yep, fossil fuels, or we get them from palm oil, which, as you probably know, is tied to some major issues with deforestation. So yeah, we desperately need a better, more sustainable way to make this stuff.
And that better way might just come from an organism we've been using for thousands of years. Yeast. But we're not talking about your average baker's yeast here. This is a special, oil-producing powerhouse.
Meet Yerba lipolytica. This yeast is what's called an oleaginous yeast, which is really just a fancy way of saying it is naturally amazing at making and storing fats and oils. And what that means is that its own natural metabolism is already set up to create the perfect building blocks for fatty alcohols. The potential is already baked right in.
But, just dropping the recipe for fatty alcohols into the yeast wasn't going to cut it. The researchers had a really important choice to make. Where inside the cell should they build this new chemical assembly line? They could try to build it out on the main factory floor, the cytosol, but that place is crowded, the product can actually be toxic to the cell, and other processes are constantly stealing your raw materials. Or they could build it in a little specialized workshop called the peroxisome, which happens to solve all of those problems.
And that decision, the one to move the whole operation into this tiny, specialized room inside the cell, that's the real game changer here. It's a fantastic example of how sometimes, to get huge results, you have to think on a much, much smaller scale.
So the big breakthrough wasn't about trying to redesign the entire yeast cell from the ground up. That would be incredibly complicated. The real genius here was way more targeted than that.
They figured out that instead of trying to work in the chaos of the main cell, they could just move their new assembly line and install it in the perfect, isolated environment that was already there. All they had to do was figure out how to get their equipment through the door.
And that special room is called the peroxisome. It's this tiny little organelle that, especially in this type of yeast, is a natural hub for processing fatty acids, which is exactly the raw material they need. It's self-contained, there are fewer competing chemical reactions, and it handles toxicity way better. It really is the perfect little high-tech workshop for this job.
Okay, so they found the perfect workshop. Now the goal was to upgrade it, to soup it up, and turn it into a super efficient production line. So how on earth do they do that?
So the first problem was just getting the main tool, this production enzyme called FAR, into the workshop. They tried just sticking a standard biological address label on it, and that kind of worked, but it wasn't great. So they came up with this incredibly clever hack. They actually fused their FAR enzyme directly to another enzyme called 3-KT that already lives inside the peroxisome. The result? The 3-KT enzyme basically acts like a personal guide, grabbing the production enzyme by the hand and walking it right into the workshop, making sure it gets exactly where it needs to go. Brilliant!
And did that little trick work? Oh yeah, just look at this chart. With the basic address label, they were getting about 452 milligrams per liter, but with their 3-KAT personal guide, that number jumped all the way up to 693. That is a huge improvement, and it proved that their fusion strategy was a massive success.
But of course, making the production line so much more efficient created a new problem, a new bottleneck. This chemical reaction needs a specific kind of energy, a molecule called NADPH, and their new supercharged assembly line was running so fast it was burning through all the available fuel inside the workshop.
So the next upgrade was to install a dedicated power supply. They engineered the yeast to make another enzyme inside the peroxisome whose only job was to generate more of that critical NADPH fuel right there on site. And the result? Well, it was just stunning. Production more than doubled again. It shot up from 0.69 grams per liter to an incredible 1.45 grams per liter. All right, so now they had all the upgrades. The perfect location, the personal guide to get the enzyme there, and a dedicated power supply to keep things running. It was finally time to see what this fully optimized microfactory could really do when they pushed it to the limit. The team took their champion yeast strain and moved it from small lab flasks into a carefully controlled 2-liter bioreactor. This let them control everything: pH, oxygen, food, super precisely, really pushing the yeast to produce as much as it possibly could over a 10-day run. And the final number was a triumph. The engineered yeast churned out a total of 2.77 grams per liter of fatty alcohols. This was a huge leap, and it really proved just how powerful their workshop engineering approach was. And when you look at the breakdown of what they made, it gets even more impressive. Not only did they make a lot, but the product was also super pure. A whopping 91% of it was exactly the one they wanted most, hexadecanol or C16. In fact, that 2.53 grams per liter is the highest amount of this specific chemical ever reported from Yerwia lipolytica, a new record. So, the big takeaway from all this isn't just about setting a new record for one chemical. It's about what this success means for the whole future of making things with biology.
What this research has really given us is a powerful new blueprint for something called organelle engineering. It's this idea that we can go inside a cell, pick one of these tiny specialized compartments that are already there, and retool it into an optimized microfactory for building all sorts of complex molecules we need, all in a sustainable way.
And that leaves us with a really exciting final thought. If we can use this strategy to brew ingredients for lotions and detergents, what else could we do? What other plastics, what fuels, what medicines or new materials could we start brewing inside these tiny, powerful workshops inside of a cell? The possibilities really are just starting to open up.